This is the third inclined plane without friction video. The aim of this video is to consider a block on a smooth incline with an internal force directed parallel to the slope and calculate its acceleration. We'll go straight into the example. A 1.6 kilogram block rests on a smooth slope. A force of 10 newtons directed upwards and parallel to the line of greatest slope is applied to the block. The slope is inclined to an angle of 25 degrees. As is usual, we will just draw out a good picture before considering the specifics of the question, so before considering parts A and B. So there's the slope. It's inclined to an angle of 25 degrees. Place the block on the slope. The block has a mass of 1.6 kilograms, so it has a weight of 1.6 g. It sits on a surface, so there's a reaction force R, and in addition to these two forces there's our 10 Newton force, which is directed upwards and parallel to the line of greatest slope, meaning that it's applied like that, in the same direction as the slope itself. We should apply the double-headed acceleration arrow. At first glance we can't really tell which way this is going to accelerate, so we'll just put it on one way, and if we're wrong the sign will just be negative, and we can fix that later. That's not hard. Now we can apply Newton's second law to this. We pick a direction in which to do that, so we'll say parallel to the slope and directed upwards. We're choosing up so we can follow acceleration. So we've got the 10 Newton force. It's fairly clear to see that that force follows this arrow, the one we've decided is positive. And we need to break the weight down into two components. So we've got this green component, which is how much the weight presses into the surface. It's the perpendicular component of weight. Then in addition to that, we have this component of weight that is parallel to the surface. If we move that along, we can see that that's parallel, but it's directed down the slope. So whatever its value is, it will be negative when we put it into this equation we're forming. The angle of inclination is always the same as the angle in the weight force triangle. This is the opposite side here, so we're dealing with 1.6 g sine 25 degrees. As we said, it was down, so it's negative 1.6 g sine 25 degrees is equal to the resultant force, and by Newton's second law the resultant is ma. We don't need to have the n for newtons. 10 minus 1.6 times 9.8 times sine 25 is equal to 1.6 times a. So the only thing we don't know there is a, so we'll just rearrange for a. Acceleration is 10 minus 1.6 times 9.8 times sine 25 all over 1.6. Acceleration is equal to 2.11 meters per second squared. So that's part A done. Before going into part B, there's some new information. The force of 10 newtons, so this force we've been working with, is only applied for 5 seconds and then removed. In part B, calculate how long it takes for the block to return to its original position. The 10 Newton force is first applied at t equals 0 seconds. Okay, well let's just get to grips with what really happens to the block before we do any calculations. At first the block starts in some low position on this surface, and for 5 seconds it's accelerated up the slope to some position, and after that the force is removed. So in the next stage of motion it still covers some ground, it's got some speed, it won't stop instantly. It makes up to some high point on the slope. At that high point it will stop instantaneously, so at that point there we'll just note that the velocity must be 0. then it's going to slide all the way back down and work its way back into the original position. That's what the question's really asking about, the block to return to its original position. Back at its original position. Okay. Well, we know how long part of this takes. We know the first bit's 5 seconds. Then we'd like to know how long the second part is. And by the second part, I mean this, going from that position there to its high point and all the way back down. We're able to treat that with just one suvat. I'll call that the second part. So for the second part, we'll take down the slope to be positive. The reason for doing that is that overall the displacement in that stage is going to be this. Right, displacement is not the distance, it's not how far it travelled, it's just the difference in, it's just the direct distance between the start and final position. So that will be S in the second part. And as that's down the slope, we can just make sure S is positive by resolving down the slope. It has a direction to it. So we don't know that yet, but we've set up for it. UVAT. Well, U, the start of the second stage, is right here. So the initial speed is whatever the final speed was after 5 seconds. So we'll note that. Speed after 5 seconds. And just to clarify on that, through this stage, the speed of the block is being increased, and that leaves it with some speed. Whatever speed it ends up with at that stage there where the highlighter stops is the speed it starts the second stage with. V, the final speed, we don't know and almost certainly won't care about. The acceleration, we don't know, but we could work it out. We could get that from forces. It's not the same, it's not the 2.11 meters per second squared that we got in the last part, and we'll see why. The time, that's what we'd really like to know. So it doesn't look great at this stage. We know almost nothing, but let's go and work out some other parts of this. So the speed after 5 seconds, well, if we were to look at the first stage, the first 5 seconds, so first stage, and we'll resolve upwards, or we'll take upwards to be positive. S, U, V, A, T. We don't really care about how far this travels just yet. The initial speed's 0, the whole problem starts from rest. V, we would like to know, because the speed at which this ends the first stage is the same as the speed at which it starts the next. The acceleration here is 2.11, because in that first stage the 10 Newton force is applied, so the value we got back here does apply to that stage. Okay, the time we're told to end the problem is 5 seconds. We know enough to work out V, and we'll need to use the equation that does not have S in it. So V equals U plus AT. V equals AT, 2.11 times by 5. V is 10.55 meters per second. So we can update that, we can put that in here, 10.55 meters per second. Again, we can also use that to update this. That was our aim, 10.55. So we've got one thing there. We would also like to know S. Well, these two stages, the first stage and the second stage, have something in common. During the first stage, this block travels up through that highlighted distance there. That's its displacement. And in the second stage, it also goes through that same displacement. It's just that in one case it's positive, or in one case it's up the slope, and in the next case it's down the slope. So if we find S for the first stage, i.e. if we find that value, we can plug that in over here and have a little more SUVAT information available. When you know 5 things, you can use whichever equation you want. So ideally you use whatever would be simple. S equals ut plus 1/2 at squared is simple here because u is 0. So we can just say 1/2 at squared. S is equal to 0.5 times by 2.11 multiplied by 5 squared. That is a distance of 26, or a displacement of 26.375. So we can update that, that's 26.375. If you keep updating the SUVAT, it's much easier than constantly trying to hunt for the information wherever it happened to be written. And again, this can be put in here. This is going to end up falling down 26.375 meters along the slope. And because we're resolving, we're taking the negative direction down the slope to be, so we're taking down the slope to be positive, we can put that in with the same sign. So getting close, 2 pieces of SUVAT information. There's this last bit here. We know the acceleration will come from forces. We know that if we think about Newton's second law, it's got ma, it's got a involved. So let's apply that. The only difference in this case is that in the second stage we don't have the 10 Newton force being applied. So we should have an equation that looks similar to this, but no 10. And notice that in this case here we're resolving up the slope, which is why that was negative. But in the case here, we're going to resolve down the slope to follow the SUVAT it goes with. So we have 1.6 g sine 25 is equal to 1.6 a. That's ma, the mass is 1.6 kilograms. G is just sine 25. Sorry, a is g sine 25. That is 4.14 meters per second squared. Again, updating as we go. 4.14. That's positive because overall we're going to be going down the slope. There's a smaller adjustment to make. The initial speed is directed up the slope, so we need to make that negative because we're working with down. Okay, we now have enough information to work out t, so we just want the equation that doesn't have v in it. So we've got to use s equals ut plus 1/2 at squared. So 26.375 is equal to minus 10.53 times by time plus 1/2 times by 4.14 multiplied by t squared. So we have a quadratic, set that equal to 0, 2.07 t squared minus 10.53 t minus 26.375 is equal to 0. So we'll get 2 values for t. T is equal to either 6.927 or minus 1.837. We know that the negative value is just not sensible. You can show it has some meaning, but it's not sensible for what we're doing here. And we've pretty much got the question at this point. It takes 5 seconds to run up the slope under acceleration. Then it carries on up the slope for a bit and then comes all the way back down to its original position in 6.927 seconds. So this takes a total of 11.93 seconds to get back to its original position. And that's the end of the question.